So let me start out just with a quick thing in reaction to the Willow announcement yesterday about random circuit sampling and toy problems, which are neat, but a lot of people don't really get. A couple weeks ago, a group called the GIMPS, which stands for General Mersenne Internet Prime Search Organization, discovered the 52nd Mersenne prime number. And for those who don't know what a Mersenne prime is, it has the form 2 to the x minus 1. So 2 to the third minus 1, 2 to the third is 8 minus 1 is 7. That's a Mersenne prime number. There are 52 known Mersenne prime numbers, and the one that was discovered a couple months ago is 2 to the 136,279,841 minus 1. It contains 42 million digits, which meant if I read a digit a second, it would take me about 15 months to read out. And the reason I'm telling you this is because in the old days, Mersenne primes were calculated using a Cray computer. And Cray used to actually have a big bulletin board and a poster board they would print out, and you could have the 31st Mersenne prime number on it. And then things changed, and for many years it went to distributed PCs. They broke the job up and they sent it out, and you could actually run variations to try to find the next Mersenne prime number. That existed for 20-some years ago, and this most recent one, it took 6 years to find this newest Mersenne prime number, was done on a bunch of NVIDIA GPUs. And I think what's interesting is that kind of shows the progression of technology at the highest end of computing. And what I'd like to challenge is, instead of Willow doing things like random circuit sampling, I'd like to see them calculate the 53rd Mersenne prime number. Shor's algorithm does something with dealing with prime numbers and products, and I think it would be really cool if someone came up with a quantum Mersenne prime number for next year's conference to really show, again, this is the next evolution in computational capability. And I think a lot more people would be much more, certainly within the HPC world, much more comfortable with a Mersenne prime number than an RCS number. Well, all that said, I just want to really just go quickly through what we're looking at in terms of looking at what we're starting to think about as utility class quantum computing systems. And the definition there, quite simply, is what can I do on a quantum system that gives me better results than what I can do on a classical counterpart? I heard the Scott Aronson's talks today, and exponential speed up and all those things are really great, and from a theoretical perspective, that's really nice to have, and those are laudable goals. But I come from the HPC community, and these are organizations that if they can get 30 or 40% performance boost on an application that matters to them for a reasonable amount of money, they're thrilled. You promise them an order of magnitude, they are absolutely apoplectic. You promise them 100x order of magnitude performance increase, and they're skeptical because they don't see that very often, if ever. So the idea here is utility class quantum can bring accelerated performance to a complicated, vexing workload in the HPC space. Doesn't require quantum supremacy, doesn't require exponential speed up. It requires performance enhancements. It requires greater fidelity. It requires bringing a better solution to a problem, even if it's only an incremental solution. If it scales, there's a rather famous example of FedEx going through a quasi-traveling salesman effort where they started to reroute all their trucks so they didn't make as many left turns. So the routes were rewired to minimize the number of left turns. And those of us who drive cars understand the tyranny of the unpredictable left turn. Big deal, right? They save $15 million a year in fuel costs by that rather simple thing. Rather incremental optimization problem, but it scales. It scales for every truck on every day of every year. And those are the kinds of opportunities that we think utility class quantum is going to bring to the sector. So let me just give you a quick overview of what we're doing from how we see the market going right now. We do an estimate every year of how big the market's going to be, and that's going to come out in March at a QEDC plenary held in, I want to say, Anaheim in a few months. And it's a data-driven one. We go out and we survey as many quantum computing makers as we can and ask them about their revenues and some of the other stuff. So it's more or less a data-driven activity in terms of market forecast. I'm not a market guy. I'm actually an electrical engineer by training and proclivities, if you will, according to my family. And so it's really, we think, a relatively realistic summation of what's going on there in the sector. And so what we came out with was about $1 billion market in 2024 for quantum hardware, software, professional services, and such. We're looking at a really compelling compound aggregate growth rate, about 22%, brings us to $1.5 billion in 2026. I now believe that number is low. I think we're going to see some much greater acceleration taking place in the next few years. In some sense, and we'll get to the graphic, I think we started to hit, there's a point in every exponential curve where when you're at the very beginning of it, it looks linear. And it takes a little bit of time to hit that curve. And I think we're going to start hitting that curve in quantum computing in the next few years. And the reason we're comfortable with that kind of assessment is we see a lot of supply side growth, and that's being driven by a number of factors. We've seen continued revenue growth by the traditional QC suppliers, and we can actually have a sector now where there are actually traditional suppliers. And we've got a representative we're sitting here in the front row here with D-Wave, the most traditional supplier of the sector. But other organizations like Rigetti and IBM have been around long enough to be kind of the old guard, if you will, of the sector. We're seeing first revenue appearances by new to market players. There's a lot of new companies out there right now who are aspiring to bring some new capability to the market. We see expanding base of domestic suppliers in nascent markets that traditionally weren't major powerhouses at the highest end of the computing, but they have said, hey, quantum computing is a greenfield kind of environment. There is no inherent advantage to say, well, we didn't dominate in classical IT, so there's no reason for us to go into quantum. That doesn't really apply here. Quantum, as I said, greenfield, new technology, lots of players that heretofore weren't really aspiring to become major classical IT nation powerhouses are looking at quantum as a way to get involved in the technology. And we're also seeing what I consider to be most important, increasing sophistication and specialization of the quantum computing stack. There are so many ways now that different companies are saying, we can do this particular slice of the stack better, whether it be instrument control to control quantum processing, whether it be optimizing compilers for laying out gate arrays, quantum gates to solve a particular problem. There's more sophistication in the stack, which means more efficiency, which means that each organization can really do a deep dive into its strengths, differentiate its product, and add to the overall capability of the sector. We're also seeing things in demand side on the rise. Every HPC site we talk to, and I can really say that with confidence, everyone is eager for quantum to come out. They have computational problems that are being unmet. Classical computers are becoming hideously expensive. The most recent Department of Energy system, the El Capitan, going into a DOE lab, $600 million procurement. It runs at about 35 megawatts. We like to use the metric that a megawatt of power costs about $1.5 million a year. So if you do the math, you spend $600 million for a computer, and you're probably going to be paying $300 to $400 million in electricity costs for the life of that system. So organizations are looking for something that not only gives them compute capability, but maybe runs at power levels that are 3 or 4 orders of magnitude less. That would be a nice way to get out of some problems. This is the chart I was talking about. We've done this estimate for 4 years. The 5th one is underway right now. And if you kind of squint a little bit, you can see that exponential curve is starting to rear out and really show what's going on. I'm not a big fan of extrapolating too far because there is always the potential of either a killer app or a quantum winter that can change the trajectory of this. But there's really some interesting stuff going on here in the sector. It's vital, it's stable, it's strong. And I think some of the inherent concerns about if there's a potential future disruption in the overall trajectory of the sector, I think have really started to go away. One of the things I like to point about is that we talk about quantum computing in its infancy, and I'd like to posit the idea that perhaps it's moving now into its teenage years, which means it's showing a little bit of growing pains. But at the same time, it's starting to reach out. It's looking to start dating and go out and meet up some partners and form some partnerships and really explore kind of the synergy of what's going on out there. And so we're seeing lots and lots of commercial partnerships. And I really think this is important because in the early days of quantum, everyone talked about full stack, or a full stack supplier, as if that was a really important thing. Well, you know what? Boeing doesn't make aircraft engines, Goodyear doesn't make cars, and McDonald's doesn't grow cattle. Okay, vertical integration is not the sine qua non of a sophisticated technology. It's really about finding the differentiating product that you do best and finding the partnerships that fill in the blanks. And so this is just, and I did this as kind of a thought experiment on paper. I spent about 20 minutes putting together partnerships just by Googling things within the last couple of months or maybe in the last 6 months or so. And you can see that a lot of the usual suspects are basically represented here in terms of reaching out from commercial partnerships, IBM and Pascal and Microsoft and Adam Carrera and Google, lots of interesting partnerships within the quantum community, but at the same time there's partnerships going on within the end users. This is, I think in some ways, a much more important partnership activity because quantum computing suppliers are figuring out what do we need to do to appeal to end users to make things happen. And one of my particularly favorite ones is JP Chase with Continuum. Every year I speak at a Wall Street conference where we do HPC and AI and quantum, and every year the lead guy from JP Chase, a former IBM guy who now heads quantum development at that facility, gives a wonderful talk about what they're up to. And every year I basically say, I'm glad you show up this year, but I'm looking forward to the year where you don't show up because that means you've turned a corner and now you want to keep everything you do secret. So if he's there next year, I'll be disappointed. The third part of the partnership, which is critical, of course, is what's going on in government. Quantum is not yet a self-sustaining activity. Government policy for R&D is great, love it, but really what matters in some cases increasingly is government procurements. Sites, we call them lighthouse sites, sites that basically legitimize a particular effort because they're doing a partnership with a quantum computing supplier, actually laying out cash, doing the research, writing papers that are viewed as objective, because that's what researchers at government labs are paid to do. And what we see here again is a wide range of different kinds of partnerships going on around the world. By the way, that blurry spot in the middle is glaringly obvious from up here, so you were right. But the key takeaway here is that everyone is involved right now in terms of the government is trying to think about the efficacy of its commercial sector and what it can do to help that commercial sector go forward. This is just a quick overview of that market study I was talking about, and the point of all this is to say, when I ask all those invasive questions about how much money did you make last year and how much did you plan on making next year, it's all due to the efforts of these various quantum computing consortia who send out a letter of recommendation to the sites we survey and say, trust these guys, they know what they're doing, continue. And fill out the request. The QEDC this year, the Quantum Economic Development Consortium, the US one is funding the survey this year, but we're getting a lot of cooperation from all these other organizations who nag their membership to say, please fill out the survey. It matters that we have good information and insight on exactly where the sector's going. This is just some quick data from the results. At the end, I'll put up my email address. If you want the full-blown survey, it's got about 30 different slides on it. But there's just some things you could point out here. Between 2021 and 2023, the number of respondents, in 2021, half the respondents had less than $50,000 US in revenues. 1/3 had no revenues. Those numbers are increasing. There's less non-revenue companies in our survey, and the companies that have revenue are all moving up the scale. So we're seeing, again, a sophistication in the sector. We always call this the Holy Trinity when we ask about major algorithms by revenue. It's mod sim, it's optimization, and AI with some cybersecurity, Monte Carlo processes. We've seen an uptake in this other category, and we kind of scratched our head about that, and we decided that what that other is more of us. It doesn't fit neatly into mod sim or optimization or AI. It's more of a hybrid kind of operation. So we're going to try to peel that back, but again, it just speaks to, I think, the developing richness of how people are trying to use quantum for their workloads. Interesting thing here when we talk about what are end user perceptions, what are your cheap motivations for getting involved in quantum, concerns with future classical performance gains. I mentioned the price issue. Basically implementing new quantum computing algorithms. They're not yet interested in reducing power and lowering computing costs. This is not a cost function just yet, but it's really, we think about innovation and exploring technology. But the key emphasis here in some sense is we need something to accelerate our existing compute workloads, and quantum offers a really good opportunity to do that, so we're keeping our fingers crossed. Because this is an EU-centric, this is a US-centric thing, and I've only got 5.5 minutes left, I just want to run very quickly through what's going on around the world that maybe people who have somewhat more of a US-centric perspective aren't aware of. There's a program right now in the EU called EuroHPC, and this basically has been in the process of developing and installing HPC centers around the EU and giving access to the entire EU science and engineering community. Well, last year they made a concerted effort to do the exact same thing with quantum. They've actually in the process of either have procured or are planning to procure all of these systems widely distributed, generally a wide range of modalities and different sites, all of them are to be integrated with the existing HPC system installed at the same location. So the EU right now is very interested in hybrid quantum classical operations. So that's really why they're trying to merge these two things. Very interesting. I will tell you unabashedly, this is kind of the trend with government policy nowadays. Every one of these procurements are unabashedly EU sites, EU suppliers. Again, it's a policy of indigenous capability to really protect, in some sense, the domestic quantum computing capability. It's a trend we're seeing more and more. Quantum is an unabashedly dual-use technology with national security concerns, and even the issues of supply chains for quantum technologies is something people are looking at. And certainly Euro HPC is kind of leading the charge in that. UK, we just heard from the gentleman from the University of Oxford recently about what's going on in the UK. But the one thing I wanted to highlight, because I thought it was a really cool way to do business, is this National Quantum Computing Center. It's basically a $40 million US test bed capability. And there's two things that I really want to point out here. The first one is you could participate in the test bed in two ways. You could either do it remotely, so you would have your machine somewhere else and you could just basically pipe into the center, or you could install a system on site. The 7 vendors that were chosen actually all chose to be on site, or were chosen because they chose to be on site. And the real goal of this was to basically say, let's put everyone in the same room for collaborative capabilities and really to encourage a UK-based supply chain. In other words, the supply base that would deal with these particular 7 systems at this test bed would all be local. And so there's a lot of this is a really interesting effort to, again, bring a nexus of compute capability in the quantum space into the UK. Now, if you're keeping track, you'll notice that they actually picked a couple of US companies to participate in this. This is one of the only government-sponsored programs I could find that actually was trying to have more than the domestic capability involved in what they were up to. Now, right now, what's going on in Japan, they don't have a really strong quantum computing base right now domestically, so they are unabashedly procuring systems from abroad. That may change soon rather than later. We see Fujitsu kind of stepping to the fore. Toshiba has done some work as well. But the bottom line is right now they are bringing in quantum computing systems from around the world, really just to get smart. Keep in mind the company, an organization called RIKEN. That's where the Fugaku system is, one of the fastest HPCs in the world. And they are very, very eager to look at quantum classical integrative capabilities there at RIKEN. One of the things we're seeing tons of right now is and roadmaps everywhere. IBM, I want to say they kind of started this, but now everybody has a roadmap. And I'm not too skeptical about roadmaps because what they do is they show long-term commitment, and they show the idea that if we don't keep our promises, we're going to be punished, and because we're laying it right out there. So I'm kind of pleased to see all the roadmaps out here, just because it shows where the sector is going, and you can start to see general progress and gauge it in a more formal way. The only reason I didn't put Google up here is because Google has a roadmap with the x-axis is in time. So it's like having a map without miles on it, not drawn to scale. But they have a roadmap too. But I think it's really important to see what's going on in terms of companies dedicating themselves to progress that says it's no longer a scientific set of problems to be overcome, it's an engineering one. And once that happens, that's when you start to see metered progress coming to the fore. So all this leads up to my initial talk, which was about quantum utility, and all the things that are leading up to getting there. And if you look at things like qubit design and manufacture, the most lowest level of abstraction in all this, one of my greatest thrills is seeing people are moving away from 99.999% fidelity to 10 to the minus 3. It's about time to start doing that, to start saying we're looking at 10 to the minus 4, 10 to the minus 5. The idea of qubits times circuit depth. The idea of how many gates can you throw at a problem during the course of that problem. It's one thing to have a lot of qubit capability, but if you can only run so many cycles of that before something goes haywire, you really, I like to say, the fastest HPC in the world, you can only run 4 instructions on it, isn't really all that useful. So I see a lot of interest right now in what's going on in circuit depth. I see interesting QC architectural advancements going on. The idea of multiprocessor QPUs, what's going on in terms of circuit knitting, the idea that I can divide up a quantum job across a number of QPUs without having to rely too much heavily on quantum computing interconnects. The maturing software stack I talked about, I'm really thrilled to see so many different avenues going on. There was, I forget which organization it is, but ANSYS is being brought into the quantum realm. ANSYS is kind of a baseline functionality in terms of modeling and simulation in the HPC world. It's great to see them involved in all this. And again, to me, one of the most interesting things is heuristics. The idea that most code that's out there in the HPC world at some point ran into a problem where someone came up with a clever hack, a way to get over a seemingly insurmountable problem. How can I trick the code? What new mechanism can I use that I better comment, because when I leave, someone's going to look and go, what the hell just happened here? I'm starting to see the idea of heuristics enter into the quantum realm. It may not be theoretically perfect, but it gets the job done. And my favorite example of this is something called Gaussian elimination. It's a way to solve series of linear equations. From a mathematical perspective, it's completely unstable. No mathematician would ever use it. But it is basically the fundamental way series of linear equations are solved. Why? Because it works. It's basically a heuristic. And I think as systems get in the hands of users and programmers, we're going to see more tweaks to the technology that actually say, okay, we may not achieve perfection, we may not be at the theoretical peaks here, but we're getting answers that work. And I think that's a really, really important aspect of all this, and something I'm going to be looking for in the next few years. So as I said, if you've got any questions or comments or whatever, because I used up all my time and a little bit more, drop me an email, and we can chat. And otherwise, that's functionally all I have to say for today. But thanks for showing up.